Hello everybody. Today we shall start with this discrete distributions. Let me recall about the discrete distribution for single random variables. So over here, in case of discrete distribution for a function of single variables, you see we had a distribution function. And if you can recall that the distribution function was actually a step function, this kind of step function, the distribution function in case of function of single random variables. And if these are, suppose this is our, maybe this is this point maybe is equal to x1, this is our maybe x2, then the next point might be x3, then we may have x4, and lastly suppose x5. So in this kind of single no variable, the distribution function that is actually capital F. Capital F is actually defined in this way. Suppose if you consider this interval xi less than or is equal to small x, strictly less than xi plus 1. In that case, or particularly if we put I is equal to, suppose I is equal to maybe 4 or 3. Suppose if we put I is equal to 3, in that case we shall have x3 less than or is equal to x less than x4. In this kind of semi-open interval, the function f of x, what was the value of this function? Say if I represent it in a different kind of color, suppose this is x3 less than equal to x less than 4. It means that x3 less than is equal to x means we shall have this kind of closed interval over here in x3 and an open interval. So x should be situated over here in this kind of semi-open interval. And so the value of the function is expected to have like this. This should be the value of the function. And what is this value? This value is actually the sum of this kind of step heights. Step heights. So that would be actually the sum of these three values. What are these values? The first value, this first value is actually our probability mass function, the value of probability mass function f1. This second value is equal to the probability mass function f2, and the third value would be is equal to the height small f3. Therefore, the value of fx, that would be is equal to f1 plus f2 plus f3. Or you can say that this value is equal to summation f k, or you can write alpha as per the notation of the book, summation f of alpha, where alpha is less than or is equal to 3. Not 3, rather over here this should be the values of alpha. Alpha should be less than is equal to x. Okay, so alpha should be less than or is equal to x3. This is the value of the density function at the first point x1. This is the value of the density function at the second point x2, and this is the value of the density function at x3. All right. And what is the lower value? Of course, it may be theoretically minus infinity. That's why in general, in case of this kind of interval, we have the definition of the function f of x. F of x is equal to this kind of summation, if alpha, where alpha less than or is equal to this one, this xi, mind it, this xi. So alpha less than is equal to xi, and over here minus infinity less than alpha less than is equal to xi. So that is actually the idea. Or if we try to impose certain inequality in terms of this index I, in that case this inequality should be written in this way, because you see this indices are represented in terms of I is equal to 1, over here I is equal to 2, then I is equal to 3, and so on. So if you want to represent any restriction over here, in that case we should have summation f alpha. Over here alpha should vary from minus infinity to at most the value 3. Over here is value 3. I is equal to, actually practically varying over here from I is equal to 1, then 2, and then 3. So similarly over here we can also write this as the summation theoretically from alpha is equal to minus infinity to I f of alpha. This was the definition in case of function of single variable. This was the definition of distribution function in case of function of single variable. And we just extend this definition in case of function of several variables. What is the definition? The definition says that this f of x comma y, over here now we shall have two real variables x and y. So these are actually the values of the random variables capital X and capital Y. So over here in case of discrete distribution, the distribution function will have two summations. One is summation over the one index may be alpha, and second one may be the index beta. So we shall have to write the mass function as equal to f alpha beta. Over here alpha should theoretically vary from minus infinity, this is alpha, from minus infinity to I, okay, and beta should vary from minus infinity to j, provided of course xi and xj, they should satisfy this kind of inequality. In that case, what would be the range of xi and xj? In that case, we shall have xi less than or is equal to small x less than xi plus 1, and what about y? Yj should be less than or is equal to small y, strictly less than y j plus 1. So that would be the distribution function in case of function of two variables, or in case of distribution, the joint distribution of the random variable x and y. So that, this was the motivation. We can say that this was the step function in case of function of single variable. Therefore, we can say now this would be the step function in case of function of two variables, and we can extend it for more than two variables as well. So this is the definition of the distribution function in case of discrete distribution. All right, and this f alpha beta, these are the mass function of this discrete distribution. And we know that in case of distribution function, we have a restriction that f of infinity comma infinity is equal to 1. F of infinity comma infinity is equal to 1. And as per the definition, what did I say? That f of x comma y is f of x comma y, that is actually equal to summation over alpha. Alpha is equal to minus infinity to I summation, then summation over beta. Beta is equal to minus infinity to j f alpha beta. So if we impose this restriction on this kind of right hand side summation, in that case what would be the condition? In that case the condition would be summation over here. We shall have to take the limit I tending to infinity and j tending to infinity. Therefore over here we shall have alpha is equal to minus infinity to infinity, and summation beta is equal to minus infinity to infinity f of alpha beta, that should be is equal to 1. Okay, this should be the this should be a necessary restriction on mass function. Okay, and of course one can prove in this case that this f of alpha comma beta or f of ij, whatever you call it, this alpha comma beta is nothing but is equal to the probability that capital X is equal to x alpha comma capital Y is equal to y small y beta. Or in your book, in place of alpha they have written I, and in place of beta they have written j. So you can also use this kind of notation, that if I j, in future we shall use this notation only, is equal to probability that capital X takes the value xi comma capital Y takes the value yj for all values of I and j, for all I and j. Okay, so this would be the mass function, and as because there is a probability, therefore this mass function should always be greater than is equal to 0 for all values of I and j. And along with this result we can have one more result which says that probability, what should I say A less than capital X less than or is equal to B, comma C less than capital Y less than is equal to D. This probability would be is equal to double summation of expressions like Fij, where the corresponding xi, the corresponding xi will lie within this kind of interval. That means A less than xi, we are not writing anything on I, but in terms of xi we are writing this inequality. A less than xi less than is equal to B, and C less than yj less than or is equal to T. So over here this kind of result would also be true. So these are some results related to discrete random variables or discrete distribution or the discrete probability distribution. So these results would be very useful in future. Remember, please try to remember these results. And now in case of I told you about the marginal distribution in defined from the two-dimensional distribution in the last class. So what would be the expression of marginal distribution function in terms of this kind of probability mass function like Fij? What would be the expression of the marginal distribution function in terms of this kind of probability mass functions Fij? Let me show you the corresponding expressions. You see, we had the marginal distribution, and what was the marginal distribution function? The marginal distribution. Okay, over here we shall have marginal distribution function. Marginal distribution function. Marginal distribution function. And marginal distribution function of x, suppose we generally write it in this way: f suffix x of x. We write it in this way. That was our notation. And by the definition, what is this? This was equal to capital F. Capital F is actually the distribution function of the joint distribution x comma y. So over here it should be is equal to capital F of x comma infinity. Y should be taken the limit infinity. And you see in the previous slide, I told you that over here we have this kind of expression, this kind of expression of a probability density function represented in terms of this probability mass function. So if we need to consider the limit y tending to infinity, in that case you see this j should also be taken to be infinity. That's why in the over here in this definition, this one, therefore we shall have this kind of result, that summation. You can write alpha first, you can write beta first. Over here I am writing beta, the second index at first. Beta is equal to theoretically minus infinity to infinity. The second index should tend to infinity, but the first index alpha, should over here alpha should be from minus infinity to I. I told you that in the previous result we have take j tending to infinity. That's why over here we have infinity. That is the upper limit of this second index beta. And f alpha beta, the mass function should come. F alpha beta. And what is the range of x? Because you see ultimately this would be a function of x alone. Therefore, we should need to specify the range of x. Over here, we should have xi less than or is equal to small x strictly less than xi plus 1. So, in this way, we define the marginal distribution function of x. And you can see over here, this can also be written in this fashion. You can now interchange their positions of alpha and beta. You see, you can write it in this way. Say summation alpha is equal to minus infinity to I, and within bracket let me write it, summation beta is equal to minus infinity to infinity f alpha comma beta. And I am going to write it in this way: summation I is alpha is equal to minus infinity to I of certain quantity. The quantity within this bracket, is represented by f x I, or it has also a different kind of representation, f I dot. Okay, in place of the second index j, we are putting dot, and this is nothing but this summation within this bracket. So if we assume that this summation within this bracket is represented by this, either this kind of notation or this kind of notation, that is actually summation from beta is equal to minus infinity to infinity f alpha beta. All right. In that case, this expression should be written like this: f I dot, and this fi dot, this is called the mass function of the marginal distribution. This is the distribution function, this one capital F suffix x, this is the distribution function of the marginal distribution, and this notation or this notation, whatever notation you follow, this is the mass function of the marginal distribution. This is the distribution function of the marginal distribution, and these are the mass functions of the marginal distribution of x, on the marginal distribution of x. So in the similar fashion, we can also define the marginal distribution for y. How to write the marginal distribution for y? In that case, corresponding distribution function should be written as f y of y, and let me quickly write the expression that will be equal to f of infinity comma y, and therefore it should be equal to firstly the summation over say alpha is equal to minus infinity to infinity, because we are taking infinity in case of x. So minus infinity to infinity, the second summation should be beta is equal to minus infinity to j f alpha beta, where this y should have this kind of range: yi less than or is equal to small y strictly less than y I plus 1. Not I, it should be written in terms of j, because y is related to this index j. So yj should be less than or is equal to y strictly less than y j plus 1. Okay, and in that case the corresponding expression, this one can also be written in this way: beta is equal to minus infinity to j f dot j. Okay, and what is this f dot j? This f dot j will have this kind of summation. It would be is equal to summation over alpha is equal to minus infinity to infinity f alpha beta, and this has this a different kind of second representation that would be f y j. So these two expressions, these are actually the probability mass function of the marginal distribution of y, and this is the distribution function of the marginal distribution of y. Got it? Now see, is it clear to you, everybody? Hello? Is this much clear? Do you have any question from this portion?
No, sir.
No, sir.
No question. Now over here we have one more idea of along with this marginal distribution, we have one more idea of independent random variables in terms of discrete distributions. Independent random variables in terms of this discrete distribution. You see, I told you earlier in the last class that what is the definition of independent random variable? Independent random variables, or random variables are also called variates. So you can also write it in this way: independent variates. What was the definition? I told you that two random variables, capital X and capital Y, these two random variables are said to be independent of each other, provided the joint distribution function of this joint distribution function capital F x into y can be represented as the product of this marginal distribution function of x. This is the marginal distribution function of x and the marginal distribution function of y. All right. So this was the definition of independent variables. Now, in terms of probability mass function, we can define the we can have an equivalent definition of independent random variables. And what is the definition? What is the equivalent definition? It says that in terms of probability mass function, you see this f alpha beta. If we say f alpha beta, we say that x and y are independent if this joint probability mass function can be represented as the probability mass function of x into probability mass function of y. That this is one representation, or you can also write it in this fashion, that if I dot into, that is, this is actually the probability mass function of x multiplied by f dot j. So these are the second representation. Anyway, whatever it is, we mean to say that if the probability mass function becomes is equal to the product of the probability mass function of x and the probability mass function of y, in that case we can prove this result. We can prove this result, and conversely this result is also true, that if this is true, then we can show this result as well. Let me just quickly show you one portion. Suppose if we suppose this result is true, this second result is true, then just take the summation. Summation over I over alpha and beta. So we can say that what is capital F of x comma y. Capital F of x comma y, that is actually the summation over double summation. Let me simply write it as summation over alpha and summation over beta. Alpha should vary from minus infinity to I, and beta should vary from minus infinity to j. Alright, so let me just simply write it summation over alpha and beta. So this would be this kind of expression, alpha beta, and then we shall have this double summation, and in terms of this f alpha beta, we can put f xi multiplied by f yj, summation over alpha and summation over beta, and you see this can be written as summation f xi, summation over alpha, and second one can be put as summation over beta f yj. So we can write it, we can separate it by brackets like this. We can separate it by brackets like this, and the first factor within the bracket, that would be nothing but is equal to f x multiplied by f y y. So we get this result, which is necessary, which is actually the definition for independence of the random variables x and y. That's why this kind of result, in terms of probability mass function, can also be considered as an equivalent definition for the independent random variables. Okay. Now let me discuss one example from the book. And what would be the geometric interpretation in case of probability mass function? You see, geometrically speaking, we can say that in a two-dimensional plane, like this kind of two-dimensional plane, maybe this is is a two-dimensional plane. The probabilities are actually maybe this one, these are the values of x. Hmm? These are the values of x. Hmm? And this might be the values of y. So you can make a grid or something like graph paper that you used in class 9 or 10, or 11, 12. So you can draw certain lines like this kind of lines. I'm just writing one this kind of few lines, and maybe this is second kind of line. So you can draw this kind of grids on all these four quadrants. And over here, let me extend it over here. Uh, and similarly for other quadrant. Now, in case of this xi, suppose this is the these are the values for this is the x1 grid, this is x2 grid, this might be x3 grid, and so on. Similarly, we can have this y1 grid, this is y2 grid, y2. Then we may have y3 and so on. So at the point xi and yj, it should represent certain points. Suppose I is equal to, at the point I is equal to 3, say x3 and y2. x3 y2, what would be the x3 y2 point? This is x3, this is the x3 grid, this is the x3 grid, and y2, this kind of point. At this kind of point, we shall have certain kind of probability mass. You can just simply consider this probability as mass as equal to certain kind of any kind of mass. You may have 1 kilogram of wheat and just distribute them. At this point, you just distribute certain amount of wheat, and maybe at other points you just distribute other kind of there may be 20 gram of weight, maybe at this point you just distribute. So in this way, altogether you will distribute 1 kg, 1 kilogram of weight. You can consider this 1 kilogram is equivalent to 1, the unit value of the probability. So maybe 100 gram is distributed over here, maybe another 200 gram is distributed over here, then 300 gram is distributed over here. So these probabilities are actually distributed on this kind of grid points. Not these are not continuous probability distributions. These are distributed at this kind of grid points. These grids may be equidistant. This may not be equidistant. These distances may be equal, may not be equal. The distance between these grid points x1, x2, x3, and so on, or y1, y2, y3, and so on, these distances may be equal, may not be equal. We are not saying anything about it, but the fact is that the over here the probabilities should be distributed on this kind of intersecting points. All right. So that is the interpretation of discrete random or discrete probability distribution. Now let me show you an example from the book. I think that would make your idea much more clear. Say consider this kind of example, this one. You see, what does it say? It says that an urn contains 4 white balls numbered 0, 1, 2, 3. All right, these are the white balls having numbers 0, 1, 2, 3. And over here we have 3 red balls. Their numbers are 0, 1, and 2, and 2 black balls. Their numbers are 0 and 1. So how many such balls are there? You have you see we have 4 white balls, then 3 red balls. 4 plus 3 is equal to 7. and we have 2 black balls. So altogether we have 9 balls, 4 white plus 3 red balls, 3 red balls, 3 red balls, and 2 black balls. We have altogether 9 balls of different colors. The random experiment consists in drawing a ball at random from the urn, and 2 random variables capital X and capital Y are defined as follows. We are just introducing the definition of capital X and capital Y. How do we define these random variables capital X and capital Y? It says that capital X takes the values 0, 1 and 2 respectively for white, red and black balls. That means if the ball drawn becomes is equal to a white ball, in that case the value of X is equal to 1. So value of X, this actually refers to white ball. Is it so? No, sorry, value of X would be is equal to 0, not 1. 0, sorry. Value of X becomes is equal to 0. So X is equal to 0 refers to the white ball. Then X is equal to 1 refers to the to this second red ball. X is equal to 1 refers to this red ball, and X is equal to 2 refers to the black ball. Okay. Next, what about Y? Y denotes the number of the ball. That means the number depicted on the ball. What were the numbers depicted on the ball? In case of white ball, we have 4 numbers, 0, 1, 2, 3. So if suppose we have white ball, in that case the value of Y would be is equal to 0, 1, 2, 3. Then in case of red balls, we have these numbers 0, 1 and 2. These are the possible values of Y. And in case of black balls, what are the possible values? 0 and 1. These are 3 possible cases of Y. So you see, Y is actually the number written on that ball. Alright. Now what to do? We have to find the joint distribution of capital X and Y and deduce therefrom the marginal distributions of X and Y. And over here we shall see, along with this result, we shall see that over here capital X and capital Y are not independent random variables. It is clear that capital X takes the values 0, 1 and 2. These are the values of capital X, 0, 1 and 2. And capital Y may at maximum, at most, take the value up to 3, 0, 1, 2, 3, or maybe 0, 1, 2, or maybe 0 and 1 in different cases. So we can say that capital X can take the values from the set 0, 1 and 2, and capital Y can take the value from the set 0, 1, 2 and 3. Alright, and that's why we are writing these grids of capital X and capital Y. You see, look at this grid. Over here, these are the X grids in along this direction. These are the X grids, and these grids are actually the Y grids. Over here, X is equal to 0 means Y-axis. This is the Y-axis. We know that the equation of Y-axis means is X is equal to 0. So this is the grid X is equal to 0. This is the grid X is equal to 1. Just a line parallel to Y-axis. This is the grid X is equal to 2. It is clear from the picture. So I'm just removing all these notations. Similarly, this is the grid. This is the X-axis. So its equation would be written by Y is equal to 0. So this is the grid Y is equal to 0. This is Y is equal to 1. Then this is Y is equal to 2, and then this is Y is equal to 3, and so on. So in this way we can define the grids of Y. Now what is the value of x and y? You see, x would take three values, 0, 1 and 2. Now if x is equal to 0, that means if we have white ball, then what are the numbers? 0, 1, 2, 3. These are the possible numbers that should be taken by the random variable y. So you see, if the first coordinate is equal to 0, then what would be the second possible coordinates? The values of y. The value of y maybe is equal to 0. So 0, 0 would be a possible choice. Then 0, 1, y may take this value 1 from this collection. So 0, 1. This is the second possible choice. Next, then 0, 2. And finally 0, 3. These are the possible choices taken by the two-dimensional random variables when x is equal to 0. And that's why you see, when x is equal to 0, this first point 0, 0, this is the first point 0, 0. It is written in a little bold fashion, although it is not clearly visible. It is written in a little bold fashion in exam, or if you want to write it in exercise book, you can encircle this one in this fashion just by a circle like this, 0, 0. Then you see, this would be, we shall have 0, 1. So this is the value. Next 0, 2. This is one value. Next 0, 3. This is another value. So we have these four values. Now you see, if y is equal to what would be the values of y? If x is equal to 1. If x is equal to 1 means the red ball. So the possible values are 0, 1 and 2. So over here, if x is equal to 1, so the first coordinate would be is equal to 1. Then the first value of y might be is equal to 0, or it might be is equal to 1, or it might be is equal to 2. These are the possible values, 0, 1 and 2. So what are the 3 points? You see, 1, 0. 1, 0 is this one. This is the point 1, 0. All right. Then 1, 1. This is the point 1, 1. And then what is 1, 2? This point. This is the point 1, 2. And similarly, in case of third ball, that means if, third color, that means when x is equal to 2, what are the values of y? 0, 1. These are the values of y, 0, 1. So the possible combinations, what would be the possible combinations? Over here, the possible combinations would be 2, 0. This is one combination, and another combination would be 2, 1. So 2, 0 means this one, and 2, 1 means this one. So that's why you can say that in this kind of two-dimensional distribution, the probability mass is distributed in these 9 points. Okay. Now, out of these 9 points, as per the question, we shall have to find the marginal distribution. So we got the two-dimensional distribution, that is actually over here distributed among these 9 points. These are the 4 points, and then this one. So in each and every such problem, you will have to identify the points at which the probabilities are distributed. So over here, the probability is distributed in these 9 points. So this is the joint probability this mass function. You can say that Fij, this probability mass function, is equal to Fij is equal to how much? You see, over here we have 9 balls, and they are randomly drawn. Therefore, the probability of each and every such draw should be is equal to 1 by 9. So in this spectrum, we can say that f of ij is equal to 1 by 9. You see it is written over here 1 by 9. And if I is equal to 0, then j should be is equal to 0, 1, 2, 3. If I is equal to 1, then j should be is equal to 0, 1 and 2. And similarly, if I is equal to 2, then j should be is equal to 0 and 1. And what are the values of the function at this kind of grids? The value of the function should be is equal to 0. No mass is distributed at this kind of at the remaining grids. So at the other grids, the value of the function should be is equal to 0. That's why you see over here it is written properly that except for f13, f22 and f23. What is the value of f13? 1 means this is 1, this is the 1 grid, x is equal to 1 grid, and this is 3. So at this point we do not have any probability mass. Similarly, we do not have any probability mass at this point and at this point. So except at these 3 points, the probability is distributed over here, and that probability would be is equal to 1 by 9. So in this way, we got the probability mass function of the joint distribution. Now, how to find the probability mass function for the marginal distribution? You see, I told you in case of marginal distribution, what is f xi? F xi, the summation should be taken on the second index, beta, f alpha beta. Beta should be theoretically minus infinity to infinity, but over here the range of second index means the y index. The range of second index is equal to 0 to 3. So we can say that over here beta would vary from 0 to 3. All right. So what would be the corresponding summation? You see, if x is equal to 0 over here, if this is the grid, x is equal to 0, then what would be the f 0 sorry, f x 0. This is the first value of x is equal to 0. So over here I is equal to 0. X if x0 should be there, and similarly for I is equal to 1, we shall have if x1, and for I is equal to 2, we shall have to find out if x2. So let us firstly compute this value f of x0. What would be f of x0? Just take this summation of all this summation over the second index. That means this kind of element, summation of this kind of elements. Over here I is equal to 0, and just add all these values. So what would be 1 by 9 plus 1 by 9 plus 1 by 9 plus 1 by 9? So altogether this value would be is equal to 4 by 9. Summation, this kind of summation. So this value would be is equal to 4 by 9. Now in case of this x, where x is equal to 1, just add these numbers at the corresponding probabilities over here. 3 into 1 by 9. These probabilities are equal to 1 by 9 at each and every such point. So 3 into 1 by 9. That means this value, this one would be is equal to 3 by 9 or 1 by 3. And what about x, f of x2? So in case of x is equal to 2, we just add this value. So that would be is equal to 2 by 9. Got it? So in this way, you can find the corresponding probability mass function for the random variable x. All right, and you can further compute similar probability mass function for the marginal distribution of y. So for marginal distribution of y, if y is equal to 0, you just add up. So the probability would be is equal to 3 into 1 by 9. Then for y is equal to 1, you just add these 3. The probability would again be 1 by 9 plus 1 by 9 plus 1 by 9. So that is actually 3 by 9. Now in case of y is equal to 2, you add up these two. So that would be 2 by 9. And for I is equal to 3, this is only one element, so 1 by 9. So in this way, you will get the probabilities, the marginal distributions of x and y. You can check over here. You see, these are the marginal distributions of x, and these are the marginal distributions of y. Marginal or the mass function of x and y. Now, along with that, if you consider just particular special case where we do not have any distribution, if you consider this value, say x is equal to 2 and maybe y is equal to 3, this one, y is equal to 3. Now for x is equal to 2, you see, if x2, I told you, is equal to 2 by 9, 2 by 9. And for y is equal to 3, you will have to add all this all along, you have to add these probabilities, but we have actually only one point, so this value would be is equal to if y3 is equal to 1 by 9. And when x is equal to 2 and y is equal to 3, what is if ij? X is equal to 2 and y is equal to 3. At this point, you do not have any probability at all. So this probability is equal to 0. We can say that if 2, 3 is equal to this 0. So you see, if 2, 3 is equal to 0, if 2, 3 is equal to 0, and this is of course not equal to if x2 multiplied by if y3. So we get a violation if we had any if we had equality for all possible values of x and y over here, then we could say that this x and y are independent random variables. But in this case, at least one set of value is there. Over here, x is equal to 2 and y is equal to 3. We got at least one set of values of x and y for which we do not have any equality over here. And that's why we can say that capital X and Y are not independent random variables. Alright, so in this way, you can verify whether these random variables are independent or not. So that's all for this lecture. Thank you for being with us.